Hello, my name is Mariano Chaves. And this I will present a work that was developed together with Professor Thomas Schwartz at the KIT in Germany. And I'm PhD student at Campinas State University under the advisement of Professor Orlando. So I'll talk about how to solve the LMA-dark NSI degeneracy with coherent nucleus scattering. Okay, just a review of the presentation. I will talk first about neutrino oscillation in the solar sector. I'll talk about the solar NSI dark solutions. I'll talk about coherent neutrino-nucleus scattering. And I'll talk about the status of LMA dark solution and about two kinds of future event experiments using stopped pion source and reactor source. So in the present status of neutrino oscillations, we have 6 parameters, and we have a mass hierarchy, and we already know 3 mixing angles of the PMNS matrix and 2 difference of mass. We have the difference square of mass of the 2-1 and of the 3-1. But we don't know the hierarchy. That is, if the third mass states is the heaviest or the lightest. And we don't know also the CP violation phase. We don't know what's the CP violation phase. It remains unknown. And together with neutrino oscillation, to explain the explanation for the solar for the neutrino that comes from the sun, is that we have some matter effects. So the matter can affect the neutrino propagate by coherent forward scattering, and the coherent forward scattering happens when the neutrino propagates, and it coherent scattering by charge current or neutral current with the electrons, quarks in the medium, and it generates an effective potential in the Schrödinger equation of the neutrino. And the potential is given by equation 2, as can you see, and that depends on the number density of electrons in the position x, for example, in the position of the neutrino. In the most general scenario, we have interaction with quarks, U and D, by neutral current, but this neutral current interaction, they cancel because some symmetries of the medium. So in the context of neutrinos come from the sun in the early of the 20s, we have in the early of the year 2000, we have 4 solutions that LMA, that is large mixing angle, SMA, that's small mixing angle, the LAW, and the VAC solution. Lately, it was proven that LMA solution was the correct one between these 4 solutions. So this is a plane of the mixing angle versus the datum square. Okay, so using this comes from solar data, and we can try to also to test this hypothesis using data in the Earth, using experiments in the Earth, and it was done using reactors for the experiment Canland, and Canland could prove that neutrino oscillations is compatible with the neutrino oscillations in the sun, the neutrino oscillations in Canland. So for Canland, is an antineutrinos coming from reactors, and they affect the we can count neutrinos in the detector, and we can see that we have a modification in the spectrum of the neutrinos. So in black we have the solar solution, and here in colored, shaded colored, we have the Canland solution, and we can see that there is a region from Canland that's compatible with the sun, but there is a region that's not compatible in the right side here, and you see that this region here comes from exact degeneracy that comes from the exchange of these 3 variables here. So if we change the quadrant of the theta 1, 2, and that's what's happening here from one side to another side, and changing the hierarchy and the CP violation phase, we can see that we have an exact solution here, and in principle, in vacuum, that's the Canlange case, it's degenerated. So in Canlange, there is no matter effects, and we have this degeneracy here, this solution here. In the sun, because of matter effects, we don't have this degeneracy, and we have only the left side solution, because the matter effects broke the degeneracy in the Hamiltonian. Okay, but these matter effects can also be affected by if you have some new interactions. This new interaction can affect the the sun, and in the simplest case that we suppose here, they can come in a form of a firm-like interaction. That I'm showing in equation 6. And in the most general scenario, we will have here, for example, we can write a matrix of potentials where VCC is the standard potential of neutrinos, and as you can see, it only affects the component 1. And here we have couplings that modulates the string of potentials in another components. And all these components come from depending on the flavor of the neutrino that propagates here. So in the off diagonal, we have flavor changing current, the current, and in diagonal is not flavor changing. And here, this couplings, I'm summing all the couplings with fermions, and they are dependent on the density of fermions in the medium. And here we are summing for quark D up, and quark down up, and for electrons. And what's interesting is that we include those effects, matter effects from new interactions in the Hamiltonian. We also have a transformation that was similar in the vacuum case that changes if you use this transformation here 9, 10, 11, 12, 13, and 14, and you can see that 12, 30, and 14 is the same as in the vacuum case, but now we need to change also the new interactions. If you do that, the equation of molecules is invariant as in the vacuum case. So we have a new degeneracy that appears when including NSI, and you can see that the degeneracy comes with a large NSI because we need to include this factor -2 here. And what happens is that if you made analysis of solar neutrinos, you can see that we have a new solution here in the right side. And this, in the left, we have the only solar data, and in the right side, we have, if you include Canland. So even including Canland, because Canland, we don't have matter effect, so it's just this equation 12, 30, and 40. So we have the same transformation as in the vacuum case. But now the solar data also have this new solution here in the right side. And this new solution is called the LMA-dark solution. So we still have the LMA-dark solution. So we have this degeneracy. This is not an exact degeneracy because you can see that these parameters here, they depend on the position, but this is an approximated degeneracy. And this is the famous LMA-dark solution. So the LMA-dark solution gives us a motivation to study large effects of NSI in different experimental contexts. And one of those experiments are scattering experiments, was the first experiment that the physics can think about. So just right here, the more general scenario, we can write equation 15 for the couplings of the neutrinos with the leptons. And it's always possible to redefine in terms of these couplings, coupling with protons and couplings with neutrons. And we can always include the electron coupling in the proton coupling, and we can write the total coupling by coupling with protons and neutrons, because always the density of protons and electrons are the same in ordinary matter. So here we made here we made an hypothesis, and in our hypothesis we suppose that the lepton flavor is independent of the quark flavor. So we include this parameter here, eta, and we have here this epsilon of eta, and this parameter here gives the strength of the interactions. And this parameter here, epsilon of, this parameter eta, it gives the strength if the protons or neutrons have more strength. And it's defined in, so in equation, you can see that in equation 12, 20 and 21, in terms of this new parameters, what's the coupling epsilon of protons and, so the key of proton, the key C of neutrons. And one can also define the nucleon effective parameter, because in scattering experiments, we'll be interested in scattering with nucleons. So the effective coupling for scattering with nucleons, if you use equation 20 and 21, will be given by equation 22. So this is y is the ratio between the number of neutrons and the number of protons. So this is an effective coupling that you see there, that will appear for nucleons. And this couplings here is related with the couplings that appears in the sun or in neutrino oscillations, because they come from the Lagrangian. So we can try to explore these couplings here, those parameters in different scattering experiments in high energy, has Charm and Chaves, so we'll have the protons and neutrons couplings. Or we can try to have some bound that's more model independent at low energy. And at low energy, if you have at very low energy, you use the Svens. And Svens is the kind of scattering where the neutrino sees the nucleon or the atom. So it's a neutral current process, because we're studying neutral current process. And it should be model independent because Svens is a very low energy scattering. So it was proposing 74, and the neutrino sees the nucleon as a whole. So the coupling that we will be using is the nucleon coupling. And then the dominant in the end, Svens is dominant for energy below 100 MeV. And equation 24, you can see here, this is the cross section where Q is this quantity here for the standard model is Z GPV, and this quantity here in equation 25. We'll call it weak charge. So, and if you include new interactions in this process here in Svens, we can see that we can write as the Q for standard model plus Z times the effective coupling that we defined before. So this will be the effective coupling, and here's the diagonal, here is the off diagonal. Remember that this quantity here is equal to 27 is the effective coupling. So the only difference between this non-standard case for the standard case is this quantity here in equation 26 for heavier for mediators that are much more massive than the energy that we are interested. So remember that this is the definition of the coupling, and we can see that this coupling here is blind, is 0, equation 27. If this eta is equals to minus the inverse of the tangent over the epsilon here, equation 28. In that case, any experiment will lead to a zero effect of NSI, and the effect will be identical to the standard model case. And this quantity here, the epsilon, depends on the nucleon. So depending on the nucleon could be blind to certain kinds of certain values of the parameter space. One of those experiments that have already mastered Svens is the coherent experiment. The coherent collaboration have mastered Svens using a neutrino beam that have anti-neutrinos of muons and neutrinos of muons and neutrinos of electrons. I will not give you details of the experiment, but they measured the Svens using cesium, iodine, and argon. So they use different nucleons. And before this work, there was this very good paper here from Esteban Coloma, Gonzalez, and Maltoni. And they put together oscillations that's in here in yellow with coherent data for different scenarios of coherent form factors and quantum factors. So you can see in the right side the LMA-dark solution versus the LMA, and you can see that if this value is positive, the LMA is better, is more favored statistically, and if it's negative, the LMA-dark solution is favored. And you can see for only oscillations, there is this region here that the LMA-dark solution is still favored. And but for you can see that we've combined with coherent, that's all this curve here for different scenarios except the yellow. We can still have some possible regions here where the LMA-dark solution still allowed, and you can see that for 2 sigma there's still some large region here between minus 35 to 0 that's still allowed. So what we did in this work was including the argon data. This work here was using only cesium iodine, and we include argon data and we include the recent released cesium iodine data together. And you can see that in black is the oscillation. In purple, if we use the data if we include argon, cesium iodine together. In orange is only argon, and in blue is only cesium iodine. So you can see that now the exclusion is more than 2 sigma for cesium iodine and plus argon. This is a good improvement that appears because we have included argon data. And why this happens? This happens because the blinding region of cesium iodine is different from the blinding region of argon. For example, here I have the contour, the 2D confidence levels for different etas, minus 37, minus 35, minus 28, and minus 20. If you remember, the blinding region of cesium iodine was minus 35. In this region, you can see that we have no bounds on the blue curve, that's from cesium iodine, but it still have from argon. And in region minus 37, you can see that we have both together constraining the problem. In black is the oscillation. I'm keeping the same pattern for the curves, for the colors and structure. And in purple, we have the combined analysis. And you can see that if you put all together, we still have 3 islands, 2 in minus 35 and 1 in minus 20. So this is the present scenario. So the question now is, can we exclude these 3 islands? And so to search for that, we search for future experiments and proposals. One of that is the ESS proposal. And the ESS is has a coherent case. It is a stopped pion source, and they can measure the electron and the muon components, and this is interesting for us, has coherent, and they propose several targets, and they propose several sensitivities to that, to use these targets to measure events. So here, the errors in the which are around 12%. And here I'm showing the results, what happens if you include the ESS measuring events together with those coherent plus oscillation data. And if you do that, we can see that for silicon, we have more than 4 sigma. Here I'm putting the best fit, the solution for the expected result for the ESS as a standard model. And you can see that silicon and the C3F8, I'm focused on them, are the best targets to exclude the LMA-dark solution. And why that's happened? This happened because the blind region for silicon is at minus 45. So it's very far from the region where we are looking for where we still have the LMA dark solution better than the LMA solution. Okay, so as you can see here, why silicon is better, because you can see that the ellipsis of the alloy region for silicon is very small. It's very small compared to the others, and is outside the regions of at 3 sigmas of the other of the combined analysis. And here I'm putting the 3 items that we have seen before. And but in that case, the 4 sigma it does not help if we arbitrarily rise the errors, because the ellipsis is not getting thinner. The ellipsis, sorry, is not get far from here. It only get thinner. So you can see here from what happens with the difference, expected difference of the chi-square, if you rise the error, and you can see it converges to a fixed value. So for ESS, we have a good result for silicon, and here we have also C2F8. So what about reactors? Because reactors, we have only electron measurement. The antineutrinos are produced, so only the electron flavor is measured. And there are 2 reactors that we consider here that are similar to CONI and CONUS, made from silicon and germanium. CONUS in Brockdorf and CONI is in Brazil, Angra dos Reis. And if you can see that if you combine the results of coherent with only the reactor result, expected result, we can help to exclude this first region here, where we have 2 islands, but not the second one. So germanium helps better than silicon in that case. And so why those reactors not so good? So this is why, because they have a wide band here. So the second region, we can see that they always touch the purple region of the island, and in the left side they can some of them they can exclude this they exclude the left island, but not the second one so good for silicon, but for germanium exclude. But can we save the reactors if we include the ESS, another different ESS measurement? So only silicon for ESS is good, but let's see what happens if we include different ESS for argon, germanium, xenonium, and cesium iodine that were not so good with the reactors. If you do that, we can see that we can exclude with them the right side region, and the left side region will be excluded by reactors. Here I put silicon, but for example, if you include the germanium case to get of the reactors, you can exclude the left side region. So the reactors, together with different targets, for example, argon, can help to solve the LMA dark side degeneracy for more than sigma either. So the conclusions, resolving the LMA dark solution is important is to enter the precision age. In the present status, the LMA dark solution is excluded by 2 sigma. Different QMU and QE measurements are necessary to look to 2 flavors. And the best option is the present proposal of ESS uses silicon target, but the reactors can help some ESS heavy target to exclude the LMA dark solution. And thank you for watching. Thank you for being here and up to here to the time. And thank you.